Hi, everybody. Welcome to PAW. Today we have Joseph Slote from Caltech, who's going to talk about Fourier analysis in quantum circuit complexity. Joe.
Hi, everyone. Thanks so much for joining. And thanks to Arena and all the organizers of PAW for this opportunity to share some work I've been doing recently. This is sort of a report on an ongoing project. Without further ado, we can take it away. I will say that, this is a little bit of a more computer science topic, so it's going to be a little bit definition heavy. We're a small group here online, so please do interrupt if anything is unclear. So here's just a bird's eye view of what we'll be discussing. So Fourier analysis, particular analysis of Boolean functions, is widely useful in classical circuit complexity. And given recent interest in quantum computing and quantum circuits, it's a natural question to ask whether similar techniques can be carried over. And this talk is kind of a first attempt to do that. An early application of Fourier analysis in classical circuit complexity was to prove that shallow classical circuits cannot approximate the parity function. And we'll kind of be taking that question and quantumizing it. And we'll find that with some effort, some interesting and related techniques from the classical approach do carry over to the quantum world. To say a little bit more about what this means, we can recall that the parity function, probably most naturally defined over bits, zeros and ones, is just the number of ones in a bit string mod 2. We'll be working over some other domains and ranges though, so you can also have parity where the range is -1, 1, in which case if there's an even number of ones, the output of parity will be 1, and if there's an odd number of ones in X, output of parity will be -1. And then, we'll also look at parity in this sense, and it's conveniently written when we work over this domain and range as just the product of the bits. And this is kind of a classic mapping in analysis of Boolean functions. It's convenient to work over one domain and range or another, and there's kind of a canonical mapping that when we're working over 0, 1, the 0 goes to a 1 when we're working over -1, 1, and similarly for 1 and -1. And then just to explain the sense in which we'll be measuring whether or not a model of computation can compute or approximate a function, we'll do it with parities. And so for functions with range -1, 1, we'll use something called correlation, which is just the inner product in the right space. So it's the expected product of f of x and, let's say, parity, where the expectation of x is uniform over all bit strings x. And if we just write it out, it's the number of x for which f of x is correct, and minus the number of x for which f of x is incorrect, if you're trying to approximate parity. So a very natural measurement there. Yeah, so let's begin with some definitions. We'll define Boolean circuits and then move on to quantum circuits as well. Excuse me. So a Boolean circuit has a kind of combinatorial description, but it then defines just a Boolean function. So the combinatorial description is that it's a directed acyclic graph, and there are n many source vertices, exactly one sink, and all the non-source vertices, or otherwise known as gates, are labeled and or not. And if they're not gates, they have in degree 1. Excuse me. The circuit C defines a function by propagating data from sources to sink. We have an example here on the left. So let's say I wanted to evaluate this function on the inputs 1, 1, 0. Well, what this means is set x1 and x2 equal to 1 and x3 equal to 0. So here we are propagating those assignments through the edges. And then if we look at that top gate, it's receiving a 1, and a 0. So the AND of 1, 1, and 0 is 0. And then each of these NOT gates will flip the value on the edge that it receives. So 1, 1, 0 becomes 0, 0, 1. And then we take the AND of those to get 0. And then the OR of those is still 0. So we find that f sub c of 1, 1, 0 is 0. If you were to flip that last bit, it doesn't take too much to realize that the output is 1. And in general, the circuit actually computes the all equal function. So it's 1 if and only if all the bits are equal. Now, we're doing complexity theory, so we want to have some measures of complexity for our model of computation. And for Boolean circuits, those are typically size and depth. So size is just the number of internal nodes, and depth is the longest directed path. The depth of this circuit here is 3. Now, many circuits define the same function. And so a typical question will be, given a Boolean function, find the minimum size and or depth of a circuit that such that f sub c is f. And these kinds of questions are deeply related to the kind of traditional big complexity theory questions like P versus NP. Excuse me. The nice thing about instead of moving from Turing machines to Boolean circuits is that we can actually prove things unconditionally. So, you know, a resolution of the P versus NP question seem to be really far out, but we can actually prove for small circuits, we can prove things unconditionally, in particular with Fourier analysis. So I'll just briefly give a peek into that. So one gem of what you'd call concrete complexity theory is the Fourier concentration of Boolean circuits. So working over -1, 1, recall that we can write any Boolean function in its Fourier decomposition, which is just a multilinear polynomial. And so it's written here, our f hats are the Fourier coefficients, and all of these are indexed by subsets of indices. So the characters are just the products of the bits in that subset, and the f hat of s is just the inner product. So very, very standard, take a function, write it out in a specific basis in function space, and the basis for us is going to be these characters, which are parities of subsets. And then having that decomposition, we can define the kth Fourier tail. So what this is it's the L2 norm squared of what you might call like the high frequency Fourier coefficients. So take all sets larger than k, and then just take the L2 norm squared of them. And the general sense in circuit complexity is that the high frequency terms, parities of large things, are harder to compute. So this is why we make the tail go in this direction. And so we have this wonderful theorem of Lineal, Mansour, and Nissan from 1993, which is that if we have a depth d size s Boolean circuit, the Fourier tail is bounded, and it's bounded linearly in S, but we have an exponential decay in the sort of smallness of the tail on the end, and so it looks kind of like a one of your tail bounds from like concentration inequalities, and in particular, if S is some polynomial in N and D is constant, then it really is honest to goodness exponential decay. So here's an example application of this powerful theorem. If we want to approximate parity with a classical circuit alone, well, we can just put k equal to n minus 1, and then instantiating the theorem, we note that the correlation, so parity itself is the highest Fourier character. So we know that the correlation of any f sub c for these circuits with parity is just the square root of that final Fourier tail. And we see here it's very, very small as n goes to infinity. And in particular, what this means is that any such circuit C approximates parity negligibly better than random guessing. So zero correlation is random guessing. Okay, so with that established, let's just talk really briefly about quantum computing. Try to keep things light, but please do interrupt if anything is unclear. So quantum computing, really all it is a complex value Hilbert space where you can do unitary transformations and then these induce probability distributions over bit strings. So to say that a little more slowly, we'll take state space to be a 2 to the n dimensional complex Hilbert space, and it'll have a canonical tensor decomposition into dimension 2 Hilbert spaces. Each of these dimension 2 Hilbert spaces represent a different qubit or bit. And so if you look at this form of canonical orthonormal basis element, it really does look like bit strings, just kind of tensored instead of producted. And states will be any element of the Hilbert space with norm 1. So states are like the quantum version of just a bit string, or like, yeah, state of computation. So what might unitary computation look like? So the first step is upon receiving an input string x, we will apply a unitary from the unitary group on dimension 2 to the n to x to get the state psi. And then we will measure it. And all this means for us is that there's some probability distribution that describes a set of bit strings we'll observe. So in particular, we observe y, which is a 0, 1 valued bit string with probability the inner product squared in this Hilbert space. So you'll note that, by definitions of inner products and things like this does define a probability distribution, which we can call d sub u of x, and it's exactly what's written there on the slide. And finally, having done that, we'll post-process with a Boolean function. So we took our x, we unitarily evolved it, we measured it, we have now some distribution over y's, and then with a sample of y in hand, we'll compute f of y for some Boolean function. And so, when the dust settles, given input x, the output of a quantum computation is just some bit sampled from the push-forward distribution of d sub u of x pushed through our Boolean function. Okay, so I have here an example computation. It's not, and maybe I won't linger on this, but it really is, it's not too bad. It's just unitary matrices, you multiply these vectors together and you get distributions. I can come back to this example if there's time, but I want to be conscious of that. One other thing that does require defining, though, is an expectation value. So I talked about how the full computation is this push forward, and it's just you get these bits as outcomes. We're very interested in the expected outcome, and we can write this in the following way. So the first line is just the definition. Second line, we've unwrapped that modulus squared and pushed the sum inside. And looking at this, we see that the inner part here is actually can be thought of as an operator. It's in fact a diagonal operator, which we'll call m sub f for any function f. And then we can rewrite this entire expression in this way. And there's a kind of notation for this that's used a lot in physics called the expectation value. We'll be using this notation moving forward. So it really is just kind of sandwich the operator inside these brackets, sandwich it with a vector and a dual vector denoted by this subscript So just as an important example, what if f is the parity function? What might the expectation value, how might you write m sub f for parity? So just writing it out directly, and we just see the definition. But if we let z equal this matrix here, z is what's known as a Pauli operator, but that's not super important. We actually see that this expression for m sub parity factors, and it factors into the tensor product of z's, one at each qubit. And in general, for any subset of n, so recall that parity is the character associated with the entire set 1 through n. For any character, we can write down m sub that character. And it's going to be the tensor where in each location, you take the identity if I is in, oh, I'm sorry, this is a mistake. This is swapped. It should be z if I is in S, and I if I, so the identity if I is not in S. Apologize for that. Okay. So that was quantum computing writ large. We do need to define the circuits that we'll be using, and I'll give a formal definition really briefly. So the whole point is that we need to restrict our unitaries somehow, because you can compute anything with a unitary. We need to add some notion of complexity. So how we're going to do that is restrict to a notion of locality. So first we'll define a layer. If we let P be a partitioning of the set 1 through n, such that every element of the partition is at size at least 2, then we can call a unitary V a layer if V factors into such a P. So each of the little v's that are being tensored together, they only act on at most 2 qubits. And then we can say a quantum circuit of depth T on n qubits is a unitary that can be written as the product of T many layers. And so visually, here's an example. The first 2 unitaries here, the first one acts on qubits 1 and 2, the second one acts on 3 and 4. Here, one unitary acts on 2 and 3, and another one acts on 1 and 4. So you'll see that in both of these cases, we've partitioned 1 through 4. And then here we have a unitary acting on a single qubit, and nothing is here. That is to represent the identity. So here's V sub 3. These are each of our layers, and then the unitary is just the product of these. So we say that this is a depth 3 circuit on 4 qubits. Okay. So thanks for bearing with me through all these definitions. We're ready to do some Fourier analysis. So let's take this theorem. So we'll let U be computed by a depth T quantum circuit, and F be computed by a size S depth D Boolean circuit. Then we'll find that the correlation between the quantum computing output here and parity here, again, is exponentially decaying. Now, the degree to which it's exponentially decaying is also controlled. I'm missing a minus sign here. There should be a minus sign there. Is also controlled by T. So you can imagine if the quantum circuit is very deep, this bound now is not very meaningful. So in general, this theorem should be taken for constant T, constant S, or sorry, polynomial size S and constant D. So there are 2 lemmas that will make this proof work. The first one I'm calling the correlation lemma. And essentially what it says is that if you're trying to approximate any function G with a quantum computation and then post-processing by some Boolean function F, it's actually equivalent to trying to approximate that post-processing F here with a quantum computation that does the inverse of what the original quantum computation does, and then post-processed with G.
Joe, I'm sorry, this is that famous result, right? Or is this a different one with a correlation lemma?
Oh yeah, this is actually the proof of this is very simple. It's essentially just Fubini. Um, so if you recall what this piece here looks like, it's really just the sum over some y's, and then what you do is you write expectations of x as a sum, and you switch the sums, and then with some change variables, you get what's written on.
Oh, okay. So this is all specific to your situation.
That's correct. That's
okay.
correct.
Okay.
Yeah. And then this is just kind of another form of this slightly more symmetric form of what's written up here. Both of these will be useful in the proof of the theorem. A second lemma is what I've called the light cone lemma. And it says that specifically when your m sub f and m sub g are those tensors of z's that I described earlier, then the trace is often zero. In particular, the trace is zero if the size of S is small relative to T. And what small means depends on the depth of the circuit. So if U is a depth T quantum circuit and the size of S times 2 to the T is less than N, this whole thing is traceless. I sort of just described the proof of the correlation lemma. It's very simple. Light cone lemma, there's kind of maybe a nice visual. I can kind of do a proof by example. So let's take a look at that.
Joe, what's the source of the name light cone lemma?
Yeah, so I'll say a tiny bit about that at the end of the sketch. It's a physics. This is a physics term. So here's a proof by example. So I've written out our operators here. We have z sub n, which is m sub parity u, and then z sub s. This is like the m sub f, where f is a character on a smaller set. Here it would be qubits 3, 4, and 5, and then u dagger. So just kind of looking at this, there's some nice geometry going on. We notice that U and U dagger, just by definition, they're symmetric along the vertical line. And in particular, if we look down here past the Z's, we notice 2 gates, and there's nothing going on in between these gates, just identities. In particular, one gate is the inverse of the other by the definition of unitary. So we can actually move these together and delete them. So this is just rewriting the same circuit or the same total unitary. And then we look again. By removing those, we now have 2 other gates that are directly facing each other, and one is the inverse of the other. So we can remove those too. Okay. Now what this means is that if we look at the bottom of the circuit, there's a Z sort of sitting alone. There's a Z tensored with the rest of everything. So the kind of main principle of this lemma is that if S is too small, if it only puts Z's on a small number of things, there's always going to be one of these Z's from Z sub n that kind of gets exposed by the deletion of these gates. So there will always be at least one Z. And bearing that and keeping that in mind, oh, actually, yeah. So keeping that in mind, we see that when we have our trace of our product here, we can write it as this factor where we've kind of argued there's always one Z. Well, the trace breaks over tensors, and the trace of Z is traceless, so the whole thing is 0. Let me go back and just explain what the heck light cone means. So in physics, there's this, we have like the speed of light, and so there's this sense in which information can't travel faster than a certain rate. And so in quantum computing, when your space is a circuit, informally what the light cone says is that the influence of Z cannot spread more than, the influence of Z can't more than double with each layer. So it kind of spreads out in this cone. And in particular, the light cone of these Z's misses these gates here. You can imagine for a larger circuit where we've constrained the depth, but allowed the width to grow, that there will be many, in fact, most gates will be deleted in the way I described. So that's kind of the principle behind why this is true. The takeaway is that this object here, when S is small, is 0. Okay, so just to recall the theorem that we're in the middle of proving, we're looking at the correlation between the quantum computation on the left, parity on the right, and we'll show that it's very small. So now we can prove this in one slide. So the first thing to do is to apply the correlation lemma to flip the quantum computation from post-processing with F to post-processing with parity itself. And then, the slide is titled Fourier analysis, so it would be illegal to not use Poincaré at some point. So here we are using it. Unwinding the definition of the Fourier transform, we see some pleasing expression develop. And using again the correlation lemma, but the second part of it, where we rewrite it in the symmetric form, we're left with the trace of ZU, which was the subject of the light cone lemma. So we find that it's 0 when S is small. Taking that into account, we can rewrite the sum itself as over only large S. And at this point, we can apply Cauchy-Schwarz to separate the function f, this Boolean function f, from the parity sort of sandwiched by these unitaries over here. And Parseval lets us to flip the second part back to the sort of standard basis. And one thing to note is that this is always going to be a bounded function. So parity is plus minus 1 valued, which means that this whole thing in expectation is bounded. And so this whole thing is at most 1. And then if we look on the left side here, this is actually exactly a Fourier tail. It's the square root of the Fourier tail past n times 2 to the minus t. And then this piece here is bounded thanks to LMN. And so I apologize again for not including a minus sign. There should be a minus sign here. Okay, but modulo that typo, that is the proof. Okay, so there was a certain the proof I gave and in the case I described is actually for a kind of quantum computation, which you might call unitary quantum computation or ancilla free. So more general quantum computation actually is, well, the generalization is very simple, but it leads to much more difficult problems. So I'll talk about that now. So just briefly, the general quantum circuits, essentially the same story as before, except now you expand your Hilbert space. So the ambient dimension of the Hilbert space will be 2 to the big N, where some big N is a polynomial of n, which is still going to be the size of your input. And as you might expect, we'll expand the Hilbert space to be 1 through big N. And then unitary evolution also will be a unitary chosen from the unitary group of dimension 2 to the big N. So how do you get strings of length little n into this world? Well, you'll always just tensor them with zeros, sort of canonically. So you take your x, you tensor it with n, big N minus little n, many zeros, apply a unitary to get psi, measure it just as before, and then you can sample the outcomes. And so now the outcomes are from this larger space, 0, 1 to the big N. And so just to introduce some notation, we can call it du star of x, and the star just is there to represent the fact that we've expanded these distributions just from these unitary quantum circuits to general quantum circuits. And yeah, and so post-processing will use a Boolean function, again, defined with this larger domain, and we'll still sample a bit from when the dust settles, we still just get a bit sample from this push forward distribution. So this seems like a small modification to the original definition, but it has some big differences. One salient one is that it's an easy exercise to prove that in the original definition for unitary quantum computing, when you view d sub u as a map from bit strings to distributions over bit strings, it's going to be a bistochastic matrix. On the other hand, d sub u star in this more general setting is only a stochastic matrix. And I mean, it's not going to be any stochastic matrix, but it's a much larger set than just bistochastic ones. And so what happens is that the previous proof technique falls apart. In particular, the correlation lemma is no longer true. Before we move on, I'll just note that for constant depth quantum circuits, you can always take that big N to be a linear function of N. So the D, we can just, moving forward, we'll just set D equal to 1. Okay. So how might we approach this larger problem? The conjecture is still the same, that constant depth general quantum circuits with constant depth Boolean circuit post-processing have negligible correlation with parity. We can't quite get there, but what we can do is we can relate the question to another big open question in complexity theory called the approximate degree of AC0, and I'll explain what that is. So if we take f to be a Boolean function, then the epsilon approximate degree of f is going to be the lowest degree function in an L infinity epsilon ball around f. So concretely, the approximate degree of f is the minimum of degree of any g such that g is within epsilon of f for all x. And so the g here, this is a real polynomial, and which is why we're allowing it to approximate the output of f by some small amount epsilon. And degree here refers to the degree of f and the degree of g written in the multilinear polynomial extended to be over r to the n to r. It's kind of a standard analysis of Boolean function setting. And so with this definition in hand, we can state this theorem, which is that if we let epsilon greater than 0 and f a Boolean function, then if the epsilon approximate degree of f decays relative to n, then we have that the best possible quantum circuit leads to a correlation with, when you're using f as post-processing, leads to a correlation with parity that's just essentially epsilon again. So what this means is that if the entire class of functions you're working with, for us it's constant depth Boolean circuits, if that entire class has this feature that it's little o of big N, then that means that then we get our conjecture proved. So we get, for epsilon small, if this is true for all such functions, then this would imply the conjecture. So this theorem is essentially a reduction from this conjecture to a conjecture about the epsilon approximate degree of constant depth circuits. And so that's exactly what we have here. AC0 is just shorthand for constant depth Boolean circuits. And there's been a lot of work on this. Some things I can mention is that there's a trivial upper bound. So the epsilon approximate degree of any Boolean function f from n bits to 1 bit is at most n, and that's just because the Fourier characters, which are parities on subsets, span the space, and there are n of them, and one of them is degree n. Some kind of positive result from Bunn, Cathari, and Thaler in last year, 2021, is that for epsilon really small, and epsilon being small is good for us, if you restrict the class of functions to be Boolean circuits with linear size, then you do get what you want. So you do get this little o of n target, which is what we needed in order to get our conjecture. But on the other hand, also last year, Alexander Shurstov proved that for any delta, we have that there's a constant depth Boolean circuit whose approximate degree, 1/3 approximate degree, is at least n to the 1 minus delta. So, you know, these bounds are not in contradiction with each other. In particular, the true approximate degree of AC0 could be something like n divided by log n. But it really, you know, both of these results are a product of huge amounts of effort, and it's a very, very difficult question. But I think it's an exciting question, and it's one that has a lot of connections to other parts of complexity theory, such as query complexity and communication complexity. I think this is probably a new type of connection between approximate degree and complexity theory, what I'm presenting here. Anything more to say? Yeah, so I can give a little bit of a sketch of why this theorem should be true, what approximate degree of the post-processing function f has to do with the ability of quantum computation to approximate parity. So what will that look like? As discussed, the idea is that we'll fix a post-processing function f, and then we'll try to maximize over all choices of du star. And here's just a cartoon of the situation. We have the world of all stochastic maps, and then there's this convex set which describes the possible du stars induced by the general quantum computation. And it is actually a convex set. It's not too hard to see that. So the first step is we will specialize without loss of generality to a special kind of du star, and that's where informally inputs have independent light cones. I'm happy to expound on that later, but the idea is that you can fix certain inputs, and if you do that carefully, parity is closed under restriction, so you haven't changed the question much, but you've greatly simplified your d sub u, and in particular, you've turned them into these things known in quantum computing as n-player non-local strategies, and they live in some convex subset of general du stars. And you know, it's a nice simplification. These are still really hard to think about, though. So there's what we actually do. So we've specialized, and now we're going to generalize. So we now relax from the space of stochastic maps that are called non-local strategies. We're going to relax them to another space of stochastic maps called non-signaling strategies. And these are much easier to define, much easier to think about, and you know, it doesn't become trivial to work with, but this is how we will be relating them to approximate degree. And to do that, we'll just make some small definitions here. We'll consider taking defining mu and nu by pushing through a uniform distribution of even inputs through a non-signaling stochastic map or strategy S, and then pushing through a uniform distribution over odd strings. And if we define mu and nu like this, then we can rewrite the correlation that we care about. So here, you know, this used to be that expectation value. We're no longer working with quantum computing exactly. We're working with these things called non-signaling strategies. So I just written it as expectation over the randomness inside script S of f of that push forward. And this whole correlation, just using the law of total expectation. If you write it out, you can switch some sums and then take these definitions, and we find that the correlation is equal to the expected value of f on this distribution minus the expected value of f on this distribution divided by 2. So this, if you're used to these questions about k-wise independence and fooling Boolean functions, these are topics in pseudo-randomness. This expression should look very familiar. The mu and nu here are examples of what you call n-wise indistinguishable distributions. I'll talk about what they are in a second, but the idea is that we've converted this question about correlation into a question about whether f can distinguish, can have a large separation between the expected value on mu and nu. So what are these n-wise indistinguishable distributions? Well, a distribution, let's say over strings of length big N, is little n-wise indistinguishable if for any subset of those indices of size little n, the projection of mu just onto those indices is equal to the projection just of those indices. So the idea is if you're a computer and you only get to see the distributions, you only get to see the indices in S from those two distributions, they will look equal. Information theoretically, they are identical. And so, yeah, so we're left with this new question. Can we distinguish k-wise indistinguishable distributions? And I've done a little bit of change of variables to match how these things are typically written in the literature, but I think it's not super important. And so here it is, this new question again: when can Boolean function distinguish k-wise indistinguishable distributions? There's a really nice answer to this actually coming from the cryptography world. So here's a theorem of Bogdanov, Ishaya, Viola, and Williamson, 2016, which is that if mu and nu, if f can not distinguish any k-wise indistinguishable distributions, mu and nu, some people call this fooling. So if k-wise indistinguishability fools f, then the epsilon approximate degree of f is also bounded by k. And moreover, it's an if and only if. So this is the proof of this is pretty short. It's actually just a linear programming duality argument. But this is the connection that's kind of pre-existing in the literature and allows us to go from our setting all the way down to just a setting, a question about approximating polynomials. So I will return just to this slide to say, here's kind of the current state of the question. We have this theorem that through a bunch of reductions and leveraging existing work, we are able to connect our approximation question to a question about the approximate degree of a function. And then we have another reason to be interested in the approximate degree of AC0. There's a lot of new exciting work, and we're sort of coming at it from above and below. And actually this bound here already gives us some confirmation of the conjecture for a subset of functions. So yeah, that's kind of where I can leave things. I'll just say thanks, and if you have any questions about anything I've discussed, I'd be happy to chat about it. It's my email, and here are the references that I mentioned if you'd like to see more. Thank you.
Thank you, Joe. Thank you so much. Questions, please?
Hi, Joe. I have a question about this approximate degree. If I take constant depth circuit, is it known what is the upper bound for the sensitivity instead of approximate degree?
I don't know off the top of my head. My immediate reaction would be to just take LMN and then use that to compute a bound on sensitivity, but I'm not sure.
Okay. Okay, thanks for the great talk.
So what's next for all of this, Joe?
Yeah. What is next? So there's a little bit. There's actually, I've written here this reduction from the main question to question of approximate degree. There's actually a much kind of more technical, slightly harder to state question, which is somewhat easier than the approximate degree of AC0 question, but still would imply the conjecture. So but the problem is it's hard to tell how much easier it is. It's still essentially, it's still an approximate degree style question. So I want to think about that. There's also a entirely different approach to this question where you actually decompose the quantum circuit as this huge exponentially large sum of classical circuits, and it's a signed sum, so it's very hard to work with. But this is another much more combinatorial approach that could also work.
Awesome. Any other questions? If not, let's thank Joe again. Thank you, Joe. I'm gonna